Hello, everyone. Welcome to another webinar in the Sustainable Webinar series that we are conducting as part of the Duruske project. So the Duruske project is between Trinity College Dublin and Bangor University. So it is across Ireland and Wales. And it is funded by EU's Interreg Ireland-Wales program. My name is Sopan Patil. I am a lecturer in Bangor University and a work package leader for the climate change impacts work package in this project. And today's topic will be on climate change and future water resources. You won't be hearing too much from me today, so I will just quickly introduce the topic and the host and the main person doing the talking today. And later on, I will be facilitating the Q&A session if you have any questions. Okay, let me move on to the next slide. Right, so before I talk about today's speaker, just to give you all a brief overview of the Duruske project. So as I mentioned earlier, this is a collaboration between Trinity College Dublin and Bangor University, and is funded by Interreg Ireland-Wales program. And the main thing that we are seeking to study in this project is how we can improve the efficiency and energy performance of the water sector. So this can be through some technological innovations, and we have work packages related to that. And we also have work packages relating to policy support and guidance. So in the previous webinars that we have had in this sustainability webinar series, we have talked about many of these issues. So things like pumps as turbines, or drain water heat recovery, and an eco-design toolkit, those different things. In today's webinar, we will be talking about mostly climate change, which in my opinion encompasses all these different work packages. And specifically, when it comes to improving the efficiency in the water sector, one of the biggest concerns going forward for the water sector is going to be about the uncertainty in the timing and magnitude of the water supply that we can get. And all the other things that we do with that water, they stem from that particular aspect. So in that sense, I believe today's talk, it really goes into the fundamental aspects of how we should be looking going forward in terms of water efficiency. So before I introduce this speaker, just a few more things about the session. So the slide presentation, it should last for around 40-45 minutes. And we will follow this by a question and answer session. As was mentioned earlier already, that this session is being recorded, and we will be making the recording available to all the participants later on. Just a few things on the on Zoom etiquette. I'm sure you all know this already, because over the last 1.5 years, we have attended so many virtual meetings. But just something if I can suggest, please do introduce yourself in the chat when you join. So we would really like to know who's in there, and that will also help later in the question and answer session. If you have a username which is not your name, but it is something else, may I please ask you to change that username so that we know who we are interacting with. That will help us a lot. Please make sure that during the presentation, you have your cameras and microphone off. And during the presentation, or even after that, if you have any questions or comments regarding what is being presented, please do use the chat function, and we will definitely respond to your question and comment. Okay, so the speaker for today is Dr. Richard Dallison. So Richard is a postdoctoral research associate at Bangor University, and he is specifically working on the climate change impacts work package. Richard also did his PhD within the Duruske project, and most of the work that he's going to be presenting today, he had done that as part of his PhD research. And as Richard will explain later in his talk, as part of his postdoc, he is now become much more ambitious in terms of the scope of the climate change research that he is doing as part of Durishke. Okay, so I will stop sharing my screen now, and Richard, you can share your screen and take over from there.
Yes, thank you, Sophan. I'll do that now. That one. There we go. Hopefully you should all be able to see that now and hear me as well, all being well. So yes, thank you for the introduction, Sophan, and good afternoon to everybody that's come along today, and thank you for joining us. As Sophan said, my name is Richard Dallison, and my research area is climate change and hydrology, hydroclimatology, and in my work over the past few years, that's really had a focus on Wales, but we're broadening that out to the wider UK and Ireland now. So today I'm going to talk about how climate change is likely to affect future water resources with a Welsh perspective, and then give the implications of that on the wider UK and Ireland scale. So in terms of what we're going to cover today, I'll first give an introduction to the future climatic and hydrological projections from literature and reports for the UK and Ireland. And we'll also look at what we studied, what research questions we aim to answer, and why. We'll then look at the methods we use for the streamflow modelling and the results we found from that modelling for Wales. And then we'll move on to look at what those results mean for water resources using a case study of hydropower. And then finally, we'll look at the broader implications for the wider UK and Ireland, the hydropower sector, and some broader water resource implications as well. So if we start with the brief introduction. So in terms of the sort of future water resources for the UK and Ireland, clearly climate change is a key driver of changes in future streamflow patterns, driven by the link between climate and river flows to the hydrological cycle. And this has an impact on the available water resource for abstraction for various different industries. And the changes we're expecting to see will alter not only average flows across a season and the year, but also the extreme flow events. So if we're likely to see increases in heavy precipitation events, clearly that's likely to bring about increases in very high flows, such as likely to cause flooding. And the opposite is true for longer periods of dry weather, when we're likely to see very low flows. And both of these changes also have impacts for water quality. We're going to discuss today all of those three factors: the average, the extremes, and the water quality as well. And understanding the impacts of these changes is important for future management of the water resources of UK and Ireland and Wales, as we will discuss. And this is important because we rely on surface waters and stream flows for a variety of sectors. I've already mentioned that we'll be looking at hydropower, but obviously the results of this work have implications for many sectors: agriculture, industry, manufacturing and commercial purposes, public water supply, as well as sectors such as tourism and leisure, where changing stream flows could impact the sort of attractiveness of sites that are based around river systems. So clearly this is an important area to study with potentially far-reaching implications, and it may have implications for the adaptation and management strategies and plans that industries and sectors have for managing their water resources moving forward. So if we're looking at both the climatic and hydrological outlook of the UK and Ireland in the future, it's quite widely accepted in various papers and studies and reports that for this region, climate change is likely to lead to hotter, drier summers and warmer, wetter winters. So that's sort of the headline for future climate change for the UK and Ireland. But alongside this, we're also likely to see increases in extreme weather and therefore flow events. So as I previously mentioned, the likelihood of more frequent and more severe flood events, and the same for droughts and low flows. And we're also, I'll come back to this several times through the presentation, likely to see an increase in seasonality. So our currently experienced seasons becoming more sort of exacerbated in the future. So we're likely to see reductions in summer and autumn flows and increases in winter and spring flows on average. And while this is true really across the UK and Ireland region, we do see some east-west differences, particularly down the centre of sort of Great Britain, the east of Scotland and east of England see slightly different patterns to this that the west of Scotland and Wales and the island of Ireland will see. So in terms of Wales specifically, the trends we're likely to see more pronounced are increases in winter rainfall and extreme rainfall events. So the literature out there would suggest that these are going to be more keenly felt in Wales and the west of the British Isles. And sort of conversely, also the increases in summer mean and maximum temperatures are likely to be stronger, have a larger magnitude of change in the west. And this obviously also brings about with it decreases in summer mean flows. So that's the sort of more pronounced trends that we're likely to see in Wales and the west compared to the wider UK picture. So in terms of the research I'm going to present today, we had two key research questions in mind. So the first of these looks to quantify the impact of future climate change on stream flow and water quality in Wales. So looking at the timing and quantity of water as well as the quality. And to do this, we studied the 5 catchments shown on the map there. So the Clwyd and the Conway in the north, the Dyfi in mid Wales, and the Tavy and the Towy in South Wales. And these 5 catchments were chosen for a variety of reasons, mainly because of their varying catchment characteristics in terms of underlying soils, topography, land use and land cover, and various other hydrometric and morphometric characteristics. They're also important catchments in terms of water supply. They supply water from those catchments supply some 975,000 people in Wales. There's 70 hydropower abstraction schemes located within those catchments. And they're also important for tourism and leisure and sit across various designations of land and protected lands, such as SSI and national parks, natural nature reserves, things like that. So they are important environmentally as well. And the second research question we wanted to answer was what impact will the changes that we model in answering the first question, what impact will that have on the available water resources and abstraction of water for hydropower? And to look at this, we took forward 2 of these 5 catchments, which I will introduce later on. So just a quick slide here on why study Welsh catchments. I quite often, when I tell people the area that I research, I sort of get the reaction that, well, you know, stereotypically in Wales, it rains all the time. So, you know, why do you need to study water resources? Surely there's plenty to go around. And, you know, while that's true for certain regions of Wales, we do see higher than average rainfalls in certain areas, especially over the mountains in North Wales. It's not true for the whole of Wales, and indeed South Wales does see, you know, average to lower than average rainfall when compared to other parts of the UK. So that is a little bit of a myth that we're, you know, super water abundant in Wales. In addition, water from Wales is used as a resource not just within Wales, but also within England. So a large amount of water gets piped every day across to the Birmingham metropolitan area and Merseyside and Liverpool as well, from large reservoirs in North and Mid Wales. So the water resources of Wales are valuable on a wider UK perspective, not just to Wales. So they are a valuable resource in that way. And as I mentioned, for water resources in Wales, important to a variety of sectors, commercial, industry, agriculture, etc. So they, are valuable to study for a variety of reasons, as they may bring about, economic impacts for a lot of different sectors. Public water supply in Wales in particular is very reliant on surface waters as well. From 95% of water supply to homes and businesses is from surface water sources such as rivers and lakes. So therefore understanding the changes that might occur is crucial for that as well. We also have hydropower. 2% of Wales' energy production is from hydropower, so there's an implication there with changing flows as well. And as I previously mentioned, the tourism sector in Wales is also built in certain areas around river systems and lakes and the water sports and things like that. So knowing how those industries might be impacted too is important. And then we've taken this catchment approach, being these 5 catchments, in order to study whether specific catchment characteristics have an influence on the hydrological response to a similar future climate forcing. So that's sort of why we're studying Wales and why we're doing it in the way we are. So if we look at the future streamflow modelling now, so to model these 5 catchments moving forward, we used a very well-known and very well-used model called the Soil and Water Assessment Tool, SWAT. And this is a hydrological model that's been used across the globe really for similar climate change impact assessment studies. So it's very well respected and widely used for this sort of research. And it was suitable for the scale of study we wanted to conduct as well. And to project forward and simulate our future flows, we used the UK CP18 data, the UK climate projections, the latest set of those. And these are a set of 12 ensemble members that are all downscaled from a global climate model, and they're all downscaled to 12 regional realizations of that model. So we modeled our stream flow in each catchment for each of those 12 realizations, and that gave us a sort of envelope of future changes and accounts for a bit of uncertainty. The analysis I'm going to show in later slides is based on the mean of those 12 outputs. But yeah, we just sort of accounted for the uncertainty in those projections in that way by modeling all 12 and then taking that mean. And that global climate model that those projections are downscaled from is based on a very worst case scenario of future climate change and global greenhouse gas emissions. So for those of you familiar with the Intergovernmental Panel on Climate Changes reports, particularly their 5th assessment report, representative concentration pathway 8.5 is that very top end estimation of future climate conditions and future temperature rises, and it's based on no downturn in global greenhouse gas emissions moving forward. So it really is a very worst case scenario. And we modeled forward to the very end of the UK CP18 data set, that's 2080. And we modeled that from the 2021 hydrological year to the 2080 hydrological year, so 60 years in total. And in terms of the analysis we performed on that model future streamflow output, for each of the 5 catchments, we studied both seasonal and annual changes. So we analysed all 4 seasons as well as the yearly time series. And we looked at this in 3 key ways. The first was average stream flow. So we took the mean daily stream flow for each year and each season and analysed that. We then looked at what we called extreme events, so high flow events and low flows. So in terms of high flow event, I've just included the graph that's on the slide here to help explain how we categorize the high flow events. So this is fictional data just to help explain the concept. So on this particular figure, we can see 3 large high flow events marked here by the green arrows at the base, and these are all high flow events that have at least one peak which falls above the dataset 95th percentile. So that's shown by the black line here, and the blue line is the stream flow volume. So we can see that each of these events has a peak, at least one peak that is above that black line. So that in our research classified them as a very high flow event. So each event starts and ends where stream flow rises from and then returns to the base flow. So stream flow in blue and base flow shown in red. And base flow is basically the portion of the stream flow that is sustained between rainfall events. So that is water that's fed into streams by what we call delayed pathways, so infiltration flow and subsurface flows, rather than overland flow and rainfall. So that's the fairly, the red line there is the base flow, that's that fairly consistent stream flow, and then the blue is the stream flow that comes from precipitation in essence. So as we can see in this graph, we have 3 events, and that is one of the first factors that we studied in terms of high flow events, and that's frequency. So the number of high flow events per year or per season and how that changes over the 60-year data set. We then looked at the severity of these events, and we did that by calculating the mean number of days per event that were above that data set 95th percentile. So we can see that in this first event was just the 1 day, but in the second event that was longer, we have 6 days in total that were above the data set 95th percentile. And even though it dips below the 95th percentile here, this is still one event as a whole because stream flow didn't return to base flow in the middle. We then also looked at the duration of the events. So we took the mean high flow event duration, in this case 12.3 days in this example here. And then finally, we looked at a second indicator of severity, and that is the maximum 1-day flow. And again, all of this was conducted seasonally and annually. So in terms of low flows, it's a lot more difficult to characterize events. So we just looked at low flows more generally without trying to identify the individual low flow and sort of drought events. So in terms of frequency for that, we looked at the number of days that were below the data set 95th percentile, so days when stream flow was below that value, so very low flows. And we also looked again seasonally and annually at the minimum 1-day flow. So 2 of the same measures we used for the high flow in reverse for low flow. And then the third area we looked at in terms of this analysis, was water quality. So for this, we looked at the concentrations or loads of 4 factors, and those were suspended sediment, total nitrogen, total phosphorus, and dissolved oxygen. And we looked at these as sort of an overall indicator of the river water quality. And I'll go into the results of each of these separate bits of analysis in this next section, which is the results of the stream flow analysis for Wales. So in terms of the future average stream flow, I'll start by saying that all of the results I'm going to present today are in this same format with these tables of with these overview tables that show the magnitude and direction of trends. So just to quickly explain how to read these. Firstly, the coloured triangles denote trends that were statistically significant at a 95% confidence level. So the hollow black and white triangles were those that were non-significant. Secondly, the triangle direction and colour, the colour for significant events anyway, indicates the direction of the trend. So blue upward-facing triangles are positive trends, increases, and the orange downward-facing arrows are negative trends, decreases. And then finally, the triangle size denotes the magnitude of the trend. So for the average streamflow results, what we can see is that the main changes are taking place in spring, where we're seeing increases across the board, and autumn, where we're seeing decreases that are statistically significant in all catchments apart from the Dovey. But overall, the annual picture is for less change. We're not seeing the same level of magnitude or significance of change for the annual average streamflow. And if we look at those catchments where there is a trend in annual average streamflow, so firstly the Dovey, we can see that these trends are driven by differences in the seasonal trends compared to the other catchments. So uniquely for the Dovey, it shows a medium magnitude and statistically significant increase in winter average flows, but we don't see the same magnitude and significance of decrease in the autumn trends. So this leads to a small statistically significant increase in the annual picture, which isn't seen in the other catchments. And if you also look at the fluid, we can see here that sort of conversely, there's a medium magnitude decline in annual average streamflow, and this is really driven by a similar magnitude decline in winter streamflows that we don't see in the other catchments. And if we move on to the high flow events to begin with, we see very similar patterns that we saw in the average flows reflected here in the high flows. The three tables that are on the slide here, we've got maximum flow, which again represents severity, and the number of high flow events, which represents frequency, and then the mean high flow event duration, which obviously represents duration. So if we look at the fluid again, we see that trends follow through from the previous slide with 1 day maximum flow and the number of high flow events declining in winter and annually, and that's a trend that we don't see in the other catchments. That's clearly part of the driving force between that annual average reduction and winter average reduction that we saw previously. Similarly, if we look at the Dovey again, we see that there's an increase in annual maximum flow and number of high flow events that isn't reflected in the other catchments, and that again relates to a combination of seasonal changes that we're not seeing in the other catchments. If we look more generally though, we see an increase generally in the severity and frequency of winter, but more so spring high flow events, and a decline in the summer events. But we see little change in summer. And aside from for the fluid and the Dovey, we don't really see that much change in the annual picture of high flow events either. If we look at the graph, the table on the right, clearly there is a lot less change happening in event duration from our results. There's a generally declining picture, but there's very little significance to those trends generally. And in terms of the number of peaks above the 95th percentile for per event, which was the other factor I introduced a couple of slides ago, we didn't find any significant changes in that measure of severity, and that particular table of results isn't on this slide. I did just want to flag those results. If we move on to the low flow events, here we see a fairly consistent picture in summer and autumn, which leads to the same trend being seen annually, and that's a decline in the minimum, in the one-day minimum flows, and little change being seen in winter and spring. And in terms of the number of low flow days per year, this is increasing annually, really being driven by increases in the number of low flow days in the autumn. So we're seeing sort of lower flow days getting drier on an annual perspective. And so if we look at water quality, the key takeaway here really is that from our results, we're seeing a general decline in water quality throughout the 4 factors studied. So we see increased concentrations of sediment, phosphorus and nitrogen, and decreased levels of dissolved oxygen in the water. And this is likely caused partly by the stream flow changes I've just outlined. So, for example, in the summer, lower flows will lead to lower levels of water for dilution, so therefore leading to higher concentrations in the water. Conversely, in the winter and the spring, we are having higher stream flows, which have greater stream power. So this leads to greater erosion of riverbed and banks. And also, if we're seeing more very heavy rainfall events, we like to see more overland flow with greater power, which will wash more sediments and nutrients and contaminants more generally into the river systems, leading to high levels there as well. And if we look at dissolved oxygen levels, this is likely a factor of 2 processes. Firstly, projected higher air temperatures lead to higher river water temperatures, and this has been shown to have a negative relationship with dissolved oxygen levels, reducing those. We also have to factor in that if there's high levels of nutrients in the water, as well as higher water temperatures, we're going to see chemical reactions running quicker and more eutrophication, which will lead to lower dissolved oxygen levels. So yes, generally a declining picture of water quality. So just to summarize the trends we've seen here before we move on, largest alterations are really happening seasonally, especially in spring and in autumn, and that's true for both average and extreme changes. If we're looking at the extreme events, we're seeing high flows increasing in frequency and severity in winter and spring, and low flows increasing in frequency and severity in the summer and autumn, but mainly in the autumn. And if you look at the results altogether, low flows are generally, the magnitude of the change in those is higher than the high flow changes. And as I said, just water quality is declining pretty much across the board for all catchments and all seasons. So if we bear those results in mind as we look at the hydropower impacts, so as I said before, we carried the study forward with 2 of the initial 5 catchments, and those were the Conway in North Wales and the Towie in South Wales. And these 2 catchments were selected because of their differing morphometric and hydrometric characteristics and their land cover, and that's demonstrated quite well in the maps shown on the left of the slide there. We can see that the Towie has much more sort of pasture land, whereas the Conway is more dominated by what we call scrubland, so moor and heathlands, natural grasslands, deep bogs, etc. And that's reflected in the table, the bottom 2 lines of the table there as well. And as we can see from the table, the Conway is it's a smaller catchment that's got a higher maximum elevation and therefore a higher slope, and that leads to it having a higher runoff ratio. So it's a more sort of flashy catchment than the Towie. It also receives more rainfall on an annual basis. So we wanted to compare these 2 differing catchments. So in terms of a brief overview of the methods for this, there are 25 run-of-river small hydropower schemes that we studied across the two catchments, 16 of these in the Conway and 9 in the Towie. And we used the first 33 hydrological years of the streamflow data we generated in the previous study. So that's 2021 to 2054. And we used this time period as sort of the working lifespan of schemes that have been implemented in the past few years, and that will be implemented in the very near future. And we categorized the schemes into 2 zone types based on guidelines from Natural Resources Wales. There's actually 3 zone types in the guidance, but the first zone type is for highly ecologically, environmentally, and hydrologically sensitive catchments, and we didn't really have a way of assessing this, so we discounted that and just used the final 2 zone types. And the schemes in these 2 zone types are categorized based on the gradient of the stream between where you abstract the water and where it's returned. And while we knew where the water was being abstracted, we didn't know the return point. So we estimated that based on the gradient of the subbasin downstream of the abstraction location in the SWOT modeling we did. And that gave us 3 zone 2 abstractions in the Conway and 4 in the Towie, and 13 zone 3 abstractions in the Conway and 5 in Towie. So more zone 3 abstractions than zone 2, more of the steeper schemes than the shallower schemes. And all you really need to know about the difference between these 2 zones is that zone 2 schemes tend to be shallower, zone 3 are steeper. The hands-off flow, so the amount of water that has to be left in the river at all times, is the same for both, but the maximum amount of water you can take is higher for zone 2 abstractions than zone 3, but the amount of water between the hands-off flow, the proportion of water between the hands-off flow and the maximum you can take is higher for zone 3 abstractions than zone 2. So this obviously has a slight impact on how the schemes are operated and the amount of water you can take from the system, from the river system. So the figure here shows the abstraction locations for hydropower within the 2 catchments. So the zone 2 abstractions are shown in the light blue circles with a dot in the center, and the dark blue circles show the zone 3 abstractions. So again, the zone 2 are the shallower schemes, and the zone 3 are the sort of steeper schemes. And as with the previous analysis, we did a seasonal annual trend analysis. We looked at 4 factors. So the first of these was the number of days per year and per season when power generation was possible. So that's when there's enough water to take us above that hands-off flow and to have enough water left over to actually turn the turbine. And that's, we've called that the days that A start is achieved. There's enough abstraction to start the turbine. The second factor we looked at was the number of days that the maximum abstraction volume as per the abstraction license conditions is reached. So we've called that the days that A max is reached. We then looked at the mean daily abstraction on days when generation was possible. So that's mean A daily. And finally, we looked at the total abstraction for each season and year and how that changed over the time period. So before we get onto the results, I did just want to show the flow duration curve for the Conway and the Towie. So the blue line, the dark blue line on this figure shows the reference period of 1990 to 2010. And the light blue line shows the future model period of 2050 to 2054, so the very end of our assessment period. And I really just wanted to highlight on this slide that we're seeing an accentuation of both the very lowest flows and the very highest flows. So if we look at a given discharge value, so let's say 1 cubic meter per second here, and for the tower, we can see it in the historical period, that flow would be being achieved at about 94% of the time in the reference period. But by the 2050s, that's only being achieved about 86% of the time. So we're seeing a decline in those low flows as well as an accentuation of the high flows as well. And those patterns that we see on the flow duration curve are reflected in the results that we see on the figures I'll present here. So if we start with the number of days that A start is achieved, so the number of days that there's sufficient flow to be above the hands-off flow and have enough water to turn the turbine, we can see that this is decreasing at an annual time step, driven by large decreases in the summer and the autumn. So there's fewer days per year when generation will be possible. However, on days that generation is possible, we're going to see a greater number of days in the winter and spring that the maximum abstraction volume is reached. So when we're hitting the limit of that abstraction license. This doesn't change the annual time series in quite the same way. The winter increases don't outstrip the summer decreases. But still, that does lead to an increase in the mean abstraction on days when generation is possible, because obviously we're seeing fewer days per year when generation is possible and higher abstraction on those days. So we're seeing an increase in the mean abstraction when the turbine is able to turn. Although again, we are seeing that seasonal shift between winter and spring and summer and autumn. However, if we look at the total abstraction and equate that to total generation potential, at an annual perspective, that is declining, driven by those summer and autumn decreases. And because due to the abstraction license conditions, we maybe can't make use of the higher flows we're seeing in winter and spring. So we see this decrease at an annual perspective, which obviously poses a potential lowering of generation moving forward, which would cause problems. So what does this mean for the wider UK and Ireland, as well as hydropower and other sectors? So if we start off with stream flow implications for the region, I said in the beginning of this talk that generally we're expecting to see very similar future climate forcing across the whole of the UK and Ireland, with some slight changes between East England and Scotland and the rest of the UK and Ireland. But broadly speaking, the results we presented are broadly applicable to the rest of the UK, although they're likely to be exacerbated if you are studying the east of England and Scotland. But they're more particularly applicable to West Scotland, West England, and the island of Ireland. Of course, it is really important to consider the individual catchment characteristics and any location differences. You know, if you've got much more snow-dominated catchments, obviously that's not going to be reflected in our Welsh work to the same degree, so that might have implications for, say, Scottish river systems. So it is still important to take account of those differing catchment characteristics if you're applying these results elsewhere. In terms of water quality, in our study, this was strongly linked to rainfall and stream flow changes. So these results are likely to be applicable across the wider region as well. Those relationships between heavy rainfall events and greater washing of contaminants into river systems, as well as lower flows causing less dilution, are clearly applicable across all catchments really. So those results are likely to be valid across the region. But clearly, in terms of the stream flow, as I said before, due to those differing catchment characteristics and that slight variation in climate forcing for the east of England and Scotland, more work is probably needed to fully characterise the streamflow changes for the whole area. And indeed, that is where our future work is heading. Sopan alluded to this in his introduction. Our current research for Darushka is looking at the impacts of future worst case scenario climate change on currently 164 catchments across England, Wales, Ireland and Northern Ireland, and we will be adding Scotland into that soon when we can access the data. And that currently includes 420 hydropower schemes as well. So when this work's completed, we should get a much better perspective on the variation in climate forcing for the wider region. So in terms of hydropower impacts, again, as has been common throughout this presentation, the seasonal changes are generally more important than the annual changes, although if we are looking at the total annual abstraction, that is likely to decline. So clearly that's important. For currently installed schemes, as well as ones that are potentially in planning, it's really important to consider the future climate changes to influence flows. So historically, schemes have maybe been developed just based on historical flows, but clearly they're going to change moving forward. So if we're looking at managing those that are already installed or planning for ones that are in the planning process, clearly looking at future climate changes that influence flows would be highly beneficial for maximizing their output and operational efficiency. And for those schemes that are in place already, current environmental regulation may prevent these schemes being optimized for future flows. Different areas of the UK have different abstraction license conditions. I presented those two sets of conditions for Wales. In some areas, the amount you can take up to that maximum abstraction allowance is higher. So clearly in those places, we're going to be able to take more advantage of those higher maximum flows and higher winter and spring average flows that we're going to see in the future. So we might need to look at those. Obviously, we still need to protect the river systems environmentally, but there is scope potentially to make more of our hydropower network moving forwards. And water quality changes could also have an impact. Clearly, if there's greater amounts of sediment that might wash into hydropower systems, that has an impact on internal moving parts if it gets through water intake screens. And also higher flows might lead to more debris, which could block the screens it intakes. That could reduce the amount of water that actually gets into the system, even in high flows. So it's also important to consider that water quality in future hydropower operation planning. In terms of just some quick broader implications, clearly the changes in the timing and quantity of future stream flows and therefore the available water resource may require stream flow dependent sectors to maybe alter their current methods in the case of industry and manufacturing where possible, or develop water allocation and management plans or water efficiency plans. They might need to be reviewed or amended. In terms of water quality, for sectors such as public water supply, but really any sector that needs to in some way clean the water it takes in from outside before they use it, there may be an increase in purification costs. It's likely to be more contaminants that might need to be removed. So that might require more chemicals or more energy to be used in that system, which will have financial, energy and environmental implications. And in terms of our Darushka project, this could have an impact on different work we are looking at. If we're thinking broadly, the energy recovery potential of from water networks, which is part of our work, clearly changing water levels could have an impact on that, and could also impact on things like payback times and the operation of pumps as turbines, which is another area we've looked at. So there's really broad implications of the work. So that's nearly it from me, but if you do want to find out more, and while you're thinking of questions for the Q&A or typing them in the chat, I will just flag that we have 2 papers on this research, one published last year on historical climate patterns that I haven't presented today, and then one on these hydropower impacts as well as public water supply. They're both open access papers, so please do feel free to go and give them a read. I'll leave this slide on the screen while we start taking questions, so you get the time to note it down if you wish. And if you do have any more questions after the session, please do feel free to email me. My address is at the bottom of the screen there. And also all the ways to contact me and the project are listed there. So with that, I will hand back to Sopan to conduct the Q&A.
Okay, thanks a lot, Richard. Right, so we do have a few minutes, at least 5 minutes or so. In case anyone in the audience has a question, you can choose to ask either through the chat functionality, or you can unmute yourself, and you can even ask it verbally. Either way should be fine for us. And it doesn't have to be a question, it can even be a comment, whatever you think about whatever Richard presented today.
I can't see the chat, so if anything does come in, please do let me know in that regard.
Hi there. Can you hear me?
Yes, we
yes,
can, Emma. Hi.
Yes. Hi. That was very interesting. In terms of water quality, so you talked about suspended sediment, phosphorus, nitrogen, and oxygen, dissolved oxygen. Are they the 4 main things you kind of look for in water quality, or is there other aspects? So for a bit of context, I'm trying to make a citizen science program. So I'm kind of interested in learning what are the key things that I should look at in terms of water quality.
Yeah, we looked at those 4 as I think I said in the presentation, as sort of key indicators of water quality. There are certainly other factors to be considered, but those 4 are particularly well modeled, or well, they're better modeled in the SWOT modeling that we conducted. We didn't have very much data to work with in terms of calibrating the model, so we just conducted a validation rather than a calibration, and those 4 factors are really the best data we could find to conduct that validation with, and that were already quite well modeled in SWOT, so we were relatively confident in how robust the output would be. And so that's the key reasons we selected those 4 really, but I suppose in terms of other factors that would be really useful to know, sort of biological contaminants, I suppose. Also these days, there's a lot of work going on with respect to sort of pharmaceuticals and things like that in river systems and waterways, and also factors such as microplastics. But we, as I say, due to the modelling and the data we could get to calibrate and validate, couldn't study those sort of factors. So we were sort of limited in that way, but I think the results we got still are indicative of the changes we're likely to see in water quality.
Okay, thank you, Richard.
Answers your question.
Yeah, so we are almost reaching at the top of the hour. So just if we can squeeze in one last question, if anyone has any.
I will say, while anybody's thinking, as I said before, if anybody does think of anything afterwards or wants to quiz me on anything or ask me about any specific, please do feel free to email me afterwards, or get in touch via Twitter or LinkedIn or anywhere. I'm happy to answer anything moving forward. But if anybody does have anything for now, feel free.
Sure. In that case, Richard, if you can now share your last slide, just the.
Yeah. So this is one of the things we wanted to flag that is going on for other colleagues in the project. So this is a citizen science project on the talking about citizen science. We're running our own on Irish household water and energy efficiency. So if anybody in our audience is living in Ireland, please do consider taking part in this. It's a short 10 to 15 minute survey on perspectives of water and energy household efficiency. It's open until the 31st of October, so please do consider taking part in this. Obviously, the bigger sample size we get, the more robust the results are, so we really are keen to engage a very broad section of society. So if you've got a few minutes to spare, please do consider scanning that QR code and filling that in for us as well.
Okay, thank you, Richard. Okay, so yeah, we're almost at 2 o'clock now over here. So thank you very much for attending today's webinar, and we will definitely make the recording available to all of you. Thanks a lot for attending. Bye-bye.
Yes, thank you all very much for listening. Thanks. Bye-bye.